So the previous video finished and we just said that this kind of really, so the internal resistance circuit is a potential divider circuit. So I've redrawn it here just to show that. Okay, look, a potential divider circuit, it's just an EMF and two resistors in series. Here we've got an EMF and two resistors in series. It's just that one of the resistors is the battery's internal resistance, which we've kind of pretended that we can separate it out from within the battery, when of course we can't do that. So this is just a model, but our model, we can still analyse it. Okay, so it's a potential divider circuit. What I need to convince you of is, if we put a voltmeter across here to measure the potential difference across big R, that is exactly the same as what we did in the internal resistance practical, where we put our voltmeter across the terminals of the battery to measure the terminal potential difference. So V term, the terminal potential difference of the battery. Those two voltmeters are measuring the same thing. I kind of need to convince you of that. Okay, so imagine we've got our voltmeter here across this one. Okay, this resistor is obviously slid around here, so this wire is kind of extended. Okay, so that voltmeter would be equivalent, I'm sure you agree, to a voltmeter attached here. Okay, so a voltmeter attached here measuring the potential difference across this one. But you could slide the leg of that voltmeter kind of along to there, and it would still be measuring the same thing, wouldn't it? Because there's no difference between whether it's attached there or whether it's attached there, assuming ideal wires. Okay, but then you could also attach it kind of across the centre there, kind of across diagonally, and that would still be measuring the same thing as well. Sorry, that's not very clear. You could slide it along to there and it's still surely measuring the same thing, and still surely measuring the same thing, and you could put it there and it would still be measuring the same thing, and even if you fold it over that way, it doesn't matter. Hopefully that's fairly convincing that this voltmeter is measuring the same thing as this one. So the terminal potential difference is really the potential difference across this resistor, which is the same as the potential difference across this resistor in the equivalent potential divider circuit. So what that means is all of the maths of the potential divider circuits that we went through in a previous video, maths of potential divider circuits, all of that applies to the internal resistance circuit. So let's just go through some of that again. What we've got in both circuits, so I'll just put a line to show that everything below the line applies to both circuits. The EMF is the potential difference across the big resistor added to the potential difference across the small resistor. In this circuit, we're going to call the potential difference across this big resistor, we're going to call it V term. So for this circuit, EMF is the battery's terminal potential difference added to, now the potential difference across the small resistor, which would be this one, I'm going to call V lost. It's called the lost volts. Because what we're saying is, just like in a potential divider circuit, the battery's EMF is shared between this resistor and this resistor in proportion to the resistances. Exactly the same thing happens in the internal resistance circuit. The battery's EMF is shared between this resistor, the external resistance, and the internal resistance in proportion to the resistances. But trouble is, the potential difference across the internal resistance then doesn't get applied across the external circuit. This is taking a share of the EMF. So some of the battery's EMF is kind of lost internally, which is why the potential difference across this is called the lost volts. So these two, hopefully you can see, are equivalent. Okay, what we can also see is we can see that just like in the previous circuit, we could say, well, what is the potential difference V lost, or in this case, what is the potential difference across R, VR? So VR is always going to be IR, because V is IR. Current going through that resistor, resistance to that resistor. V lost is exactly the same thing. IR. So we can substitute that into this equation. So EMF will be the terminal potential difference added to IR. And then what we'll do is we're just going to change the signs of some things a little bit. We'll say that, we'll put this on, I'm just going to switch the order of these two. And I'm going to substitute it to the other side. So I'm going to do minus Ri on both sides. So minus Ri plus the EMF gives you V term. Now that looks a bit weird, but this is exactly what we plotted in the internal resistance graph. We plotted, when you change the resistance in the circuit, we plotted current on the x-axis and the terminal potential difference, the potential difference across the terminals of the battery on the y-axis. So that goes on the y-axis, and you can see that this has the form, the gradient is going to be negative, and the internal resistance is a constant, so it's a constant gradient, so it's a linear graph that's negative with a y-intercept. So that explains the shape of that graph that we got in the internal resistance practical. Okay, it's a negative graph, and the gradient actually gives us the internal resistance of the battery. The y-intercept gives us the EMF of the battery.